Energy-momentum tensor. We have learned that energy and mass are equivalent through E equals gamma mc squared. Let me now give an overview of the energy-momentum tensor that we are about to explore. In his general theory of relativity, Einstein proposed that gravity is not a force, but rather a manifestation of the geometric structure of spacetime. He conceived that gravity arises as a result of massive objects, those possessing enormous energy, mass, curving spacetime. The energy-momentum tensor is the mathematical expression of that true nature of gravity. It forms the right-hand side of Einstein's gravitational field equation. Here we encounter a physical quantity called a tensor. Its full meaning will gradually become clear as we proceed, but let me briefly mention it here. A tensor is a physical quantity that, like scalars and vectors, does not depend on the choice of coordinates. A scalar represents a single physical quantity, magnitude alone, while a vector represents two aspects, magnitude and direction. A tensor is a higher-order mathematical expression that encompasses both of these and can represent an even richer set of physical quantities. Energy-momentum tensor, the fluid element model. Let us consider an infinitesimal fluid element as a model for the energy-momentum tensor. We adopt a perfect fluid to represent our universe. This is a fluid that is non-viscous, non-heat conducting, and isotropic. Remarkably, the universe on large scales is well described by precisely this idealization. We work in the proper time frame. Think of it like a first-person perspective in a VR game, viewing everything from the standpoint of this fluid element. In this frame, both ourselves and the fluid element are always located at the origin O. This frame is called the co-moving frame, and we will use this term from here on. The coordinates of the fluid element in four-dimensional spacetime are ct, x, y, z, or, equivalently, x0, x1, x2, x3. The energy momentum of the fluid element is given by p mu equals p0, p1, p2, p3. We have established that the relativistic energy is Cp0 equals E equals gamma mc squared in the co-moving frame, V equals 0, and therefore gamma equals 1, giving P0 equals E over C. The relativistic four momentum is given by We now introduce the following mathematical expression as the energy-momentum tensor of the four momentum, T mu nu. Since this tensor represents both energy and momentum, we take the time component of the four momentum as Cp0 equals E. The energy and momentum that constitute the tensor are therefore given by This carries two upper indices, mu and nu. The index mu runs over the momentum components 0, 1, 2, and 3, while nu runs over the spacetime coordinates 0, 1, 2, and 3. It is therefore a physical quantity consisting of 4 times 4 equals 16 components. Broadly speaking, it describes which components of momentum are flowing in which coordinate direction. Let us now look at each component in detail. Before working specifically in the co-moving frame, let us first build an intuitive understanding of what each component of the energy-momentum tensor represents. This basic idea applies in any inertial frame. T00. This represents the flow of C, P0 equals E equals gamma mc squared in the x0, i.e. the CT direction. T01. This represents the flow of C, P0 equals E equals gamma mc squared in the x1, i.e. the x direction. The same applies to T02 and T03. T10. This represents the flow of the P1, i.e. the px component of momentum in the x0, i.e. the ct direction. The same applies to T20 and T30. Spatial components T11, T12, T13. T11 represents the flow of P1 equals Px in the x, 1 equals x direction. T12 represents the flow of P1 equals Px in the x2 equals y direction, and T13 represents the flow of P1 equals Px in the x3 equals z direction. The same logic applies to the spatial components Tij in terms of which momentum component is flowing in which direction. However, the spatial components carry additional physical meaning, and therefore do not necessarily vanish even in the co-moving frame. The remaining spatial components follow exactly the same pattern. Please regard this as a first step, an introductory understanding of the physical meaning of the energy-momentum tensor. Let us now summarize the overall picture. We now work in the co-moving frame. As the next step, we want to express these energy-momentum quantities at a single point in four-dimensional spacetime, that is, at the fluid element. To do this, we convert them into energy density and momentum density. In the co-moving frame, the energy, mass, and volume are all at rest. We denote them as the rest energy E0, the rest mass M0, and the proper volume V0, respectively. Since V equals 0 and therefore gamma equals 1, the energy reduces to E equals gamma mc squared, which in the rest frame reduces to E0 equals m0 c squared. Dividing this by the proper volume V0, we obtain the energy density epsilon naught. We derive the momentum density in the co-moving frame. Here we denote the momentum density as pi I, dividing the momentum pi by the proper volume V0. Since V equals 0 in the co-moving frame, the momentum density vanishes. We have derived the energy density and momentum density in the co-moving frame. The proper density ρ0, appearing in these expressions, is given by the rest mass m0, divided by the proper volume V0. At first glance, one might expect these quantities to vary between inertial frames due to Lorentz contraction. However, they are all Lorentz invariant. They take the same value in every inertial frame. Let us verify this. These are indispensable building blocks of the energy-momentum tensor and must be identical in all frames. Rest mass. The rest mass is defined as a Lorentz invariant. That is, it takes the same value in any reference frame based on experimental observation. The theory adopts this as part of its foundational framework. 1. Historical background. Moving objects become heavier. In the early days of relativity, during Einstein's own era, it was thought that mass increases with motion. This quantity was called relativistic mass, written as m equals gamma m0. Under this interpretation, mass itself was considered to vary depending on the velocity of the observer and was therefore not invariant. 2. Modern definition. Mass is fixed as an invariant. In modern physics, the term relativistic mass is rarely used. The reason is that clearly distinguishing between energy E and mass m is overwhelmingly more convenient and elegant for describing physical laws, in particular, tensors. The modern definition is as follows. Mass m, the energy a body possesses when at rest, E0 equals m0 c squared, which gives m naught equals E naught over c squared. This is an intrinsic property of the body and does not change regardless of the reference frame. It is a Lorentz invariant. Energy E, a quantity that varies depending on the reference frame. As velocity increases, energy increases. In other words, rather than interpreting this as mass changes, the definition has been unified so that we interpret it as energy changes. 3. The relationship with experiment. Why can we say mass is invariant? This is not simply a matter of it is invariant by definition. Behind this definition lies unshakable experimental evidence. Experimental fact: no matter how much a particle is accelerated, for example in a particle accelerator, its identity never changes. An electron, however fast it travels, always retains its properties as an electron. Confirmation of invariance. By measuring the total energy E and momentum P of a particle and performing the following calculation, experiment consistently yields a constant value independent of velocity. This follows from an intermediate result in our earlier derivation of energy. In deriving the relativistic energy, we define this expression as shown. We now rearrange it as follows. The m naught on the right-hand side is precisely what we call mass. While E and P individually vary depending on the inertial frame, the combination E squared minus PC squared always equals m naught c squared, all squared, and remains invariant across all inertial frames. This has been confirmed by an enormous number of high-energy physics experiments. This constant value as the quantity that characterizes the true intrinsic nature of the object was defined as mass, rest mass. By adopting the definition that mass is invariant, physical laws become far easier to express in a form that is independent of the choice of coordinate system, that is, in covariant form. This is why relativity is both mathematically beautiful and enormously powerful. Proper volume. Volume in general undergoes Lorentz contraction depending on the velocity of the observer, changing as v equals v naught over gamma. In other words, volume in the general sense is not an invariant. However, the moment we use the term proper volume v naught, it is defined as referring to the following specific quantity: the volume measured in the coordinate system in which the object appears to be at rest, that is, the co-moving frame. No matter which observer is looking at the object, if asked what is the proper volume, everyone answers with the value measured by someone moving together with the object. This is the agreed rule. Since the reference value is thus fixed to a single unique measurement, it becomes invariant as a scalar quantity. Relationship with particle number, intuitive understanding. The most intuitive way to understand this is to focus on the number of particles. The total number of particles, n, dimensionless, contained in a given piece of matter is an invariant that does not change regardless of the observer. Here we define the proper number density n, not as the number of particles per unit volume in the co-moving frame. N equals n naught times v naught. N is an invariant. The number of particles does not change. N naught is an invariant because it is defined as measured in the co-moving frame. Therefore, v naught equals n over n naught is also an invariant. Summary. Why can we say proper volume is invariant? The measured volume v differs from observer to observer and is therefore not invariant. The proper volume v naught, on the other hand, comes with a fixed measurement condition, measured by someone moving together with the matter, and therefore refers to the same value for every observer. It is an invariant. In physics, any quantity preceded by the word proper refers to the value measured in the most natural frame for that object, its rest frame. Such quantities are automatically treated as Lorentz invariants, scalars. Proper density. The proper density is the true density as measured by an observer moving together with the matter, that is, in the comoving frame. Rho naught equals m naught over v naught. Since both the rest mass m naught and the proper volume v naught are individually Lorentz invariants, their ratio rho naught is naturally also a Lorentz invariant. In relativity, lengths and volumes appear to change due to Lorentz contraction depending on the state of motion of the observer. Since the volume appears smaller, a stationary observer would measure a higher density even though the mass of the object has not changed. This means that if we were to use the density as seen from an arbitrary frame, its value would differ from observer to observer, which is highly inconvenient for describing physical laws. We therefore use the proper density rho naught, the density measured in the rest frame of the matter, as the quantity that represents the intrinsic properties of the material itself. The proper density is indispensable for writing physical laws in a coordinate-independent form, that is, in tensor formalism. The energy-momentum tensor we are currently deriving is also described in terms of the proper density.